Get your clickers out. I got a couple questions. We'll see what we picked up from last lecture and continue on with heat. And while we're logging in and whatnot, Mackenzie? Did you want to discuss that ball more?
Yeah, after class.
Sure. Well, did it make more sense? Yeah, it makes sense. But yeah, while people are logging in, it's basically the airflow around the ball, right?
I just want to make sure I understand it correctly. So
Yeah.
it'll take a few minutes.
You bet. You'll just have to give me a few minutes to get out of the way. And then, you have a class right after?
No.
We're set. Okay. So let's see if you, through your reading and last lecture, know what heat is. Ten, 9, 8. Haven't logged in yet?
Yes, my internet connection is being.
Oh. Well, that was just because most people had that blank look. And let me know when it comes up. Tell me when. Are you friendly reminder again? If you do ResponseWare, they suggest you connect rather than your. Although this semester Uconnect's been a little flaky. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. We got 27 players today. Okay, some of you think it's B, but most of you think it's C. All right, thermal energy is what? Internal energy. That's the one I wrote in the book, and the author said up until now, he said thermal energy. And if I were to guess any other one than the correct answer, that's what I would have guessed. Because people in the real world, and even scientists, interchange heat and thermal energy a lot. I've probably even done it up till this point. However, now you know. Thermal energy is more accurately described as internal energy, which is the total energy that atoms and molecules have, from translational kinetic, but also rotational, vibrational, potential, and anything else. It's everything. We'll call it internal energy. That's not heat, because objects can't contain heat. They can contain internal energy, but they don't contain heat. Heat is energy in transit. It's that internal energy that flows from hot to cold. And it only flows under what condition? If there's a difference in temperature. Because if things are the same temperature, no internal energy wants to flow one way or another. But while I'm on this question, internal energy does not determine which way it flows or if it flows. I'll repeat that. Internal energy does not determine whether it flows or in which direction. The temperature does. There must be a difference, just like we didn't notice pressure much, the air in the room, until there was a difference in pressure, and that caused the fluid to flow. Well, that's right. Was that your shoe? Yeah. Good answer. That was fun. So if you have a difference in temperature, that'll cause internal energy to flow. We call that heat, energy in transit. And I was going to say something. Oh yeah, historically, one of the units for heat. Heat is what type of, has what form? Is it a mass, velocity, force, volume? I just said it. What's the units for heat? It would be, it's an energy, right, and the units for energy are joules. That's what I was getting at. It's just, energy in transit, like work is joules, potential energy is joules, kinetic energy is joules, heat is joules. Historically, they used, and a lot in the United States, calorie. That's just another unit for energy. 1 calorie is about 4 joules, to give you an idea. And when you look on your food, You can see how many calories there are? That's telling you the internal energy content. However, in food, they use a big C instead of a small c. And 1 food calorie is actually 1,000 physics calories. So the calorie we use as a unit, scientists, and I'm just talking about, when it says 150 calories on your food, it actually means 150,000 real calories. And then multiply that by 4.184 and you get how many total joules it'd be. So you can gauge how much internal energy there is in your food. Now, somebody had a question.
Well, I was saying, is it incorrect to say that something is hot then?
No, because hot is a measure of temperature. And temperature is a measure of what? Do you remember? There were 3 things. What determines something's temperature?
Average translational kinetic.
Oh, you get a gold star. The average translational kinetic energy.
Okay.
So when you say something's hot, that tells me right away that the molecules are moving at a certain speed, on average. Because some are moving faster, and some are moving slower, and they'll speed up and slow down. But on average, they have a certain speed. And it's that determines the kinetic energy. But it's the translational kinetic energy we're concerned with. Because they can be rotating or vibrating, but that doesn't matter. That doesn't determine temperature and how hot it is. So yeah, you can say something is hot. You can say something is cold, and that gives you a gauge about its average translational kinetic energy, not internal energy. So temperature is just that. Heat, internal energy is the total energy, and heat is the transference of that internal energy from a hot object to a cold object. It always goes from hot to cold, naturally.
Could you explain again why, like the sparkler, like the book said, those sparks are like 2,000 degrees, but it doesn't.
Yeah.
Why is that?
So-
I don't get that.
And we're covering that more today. It'll be clear by the end, that's for sure. But right now, because you're on it, they're hot. They have a high temperature. Granted, so we know what that means now. And that's true. But yeah, I don't burn myself. Why? They must not contain much internal energy. Or there's not enough internal energy transferred to me in that process to hurt me. Because it's heat that's transferred, that internal energy. Hot is just a measure of, temperature is just a measure of how hot it is in the first place.
Does it have something to do with mass?
Absolutely. These are very small.
All right, well, speaking of that, what is fire?
What is fire?
Yes. What state of matter is it?
Oh, what state of matter? Plasma, which is discussed in the end of the chapter. I'm not dwelling on it. Plasma is like an electrified gas. The closest, you got solid, liquid, gas. It's mostly like a gas, but it's electrified. It has a bunch of charge. It's like atoms that have been stripped of their electrons, so they're ionized. And they can have a lot of energy that way. Plasmas are your microwave-conformed plasmas inside. I don't know if you... I stick lots of weird things you're not supposed to in a microwave. But one example is you can put a candle in a microwave, and I've actually trapped a plasma ball underneath a Pyrex glass. Anyway, you can YouTube it too. Other examples of plasma, and they're in your book, but on the sun, neon lamps, those plasma balls, they're lightning balls. You touch them and it looks like a little lightning contained in the ball. That's plasma. There'd be plasma in a lightning strike.
TV?
Plasma TVs. All the little cells, your pixels, are full of plasma. Electrified gas inside, yeah. All right. So when heat's added to a system, what does the temperature of the system do? What can it do? So we're adding heat. I'll give you. That's the internal energy that's transferred to it. That energy goes into this new system. What happens to the temperature of that new system, or what can happen to the temperature? That's what it's asking you. In other words, you add energy to something, what happens to it? 10, 9, 8, 7, 6, 5, 4, 3, 2. We got more players. All right. 1. Ooh, we're split. So you guys either think it rises or it may or may not rise. Somebody that thinks it may or may not, you obviously think it can. What's a condition where you don't think it could or would? Because you obviously are thinking of something. What's a condition where the energy goes in but the temperature doesn't rise? What are you thinking then? Those of you that answered B. You don't want to tell me? Do you want to tell your neighbors?
Thought of like cold and hot water.
Cold and hot water?
Yeah. So if you have like a bunch of hot water, I don't know. I just felt like if you added cold water to it, it may.
So if you take.
Water or
In general, when you take something hot and you take something cold and you put them together, they're going to come into equilibrium because there's a difference in temperature. So internal energy will flow, heat will transfer. So the hot will get colder, generally, and the cold will get warmer, generally, because it absorbs internal energy and this one gives it up. Can you think of an example where something changes its gives up internal energy or gains internal energy, but its temperature does not change? Okay, you have to think back to your chemistry or from reading the textbook. Because if not, I don't know why most of you answered B. That's why your gut, right?
I'm not sure, but does this have something to do with exothermic and endothermic reactions?
Exothermic and endothermic. Fancy words for endothermic means it gives up internal energy. No. Other way around. Exothermic is giving it up and endothermic is taking it in. Yeah, fancy words just for that. Well, all right, I'll give you the answer then. The correct answer is B. It says there, the first answer is correct only if the substance doesn't change phase. Think of phase changes. There's a whole chapter to that we're not covering, but you guys are familiar enough with phase changes. When ice melts, it's going from solid to liquid. Does it take energy to melt, or does it give up energy to melt? It takes energy. You got to put heat in, right? Energy in, transfer heat to it. It warms up. But ice is freezes at 0 degrees Celsius. It turns into water at 0 degrees Celsius. So the temperature didn't change. But energy was put in. Where'd that energy go? To break the bonds. And if you didn't know that, you at least knew where the energy did not go, into average translational kinetic energy. Otherwise, the temperature would have gone up. So the molecules still have other forms of energy. That's internal energy. That's total. And so energy can go into one of those forms, make it rotate faster, or breaking bonds. But if it does not go into increasing the average translational kinetic energy of the molecules, the temperature doesn't change. And that's what happens in phase changes, both directions.
So is that what that 4 degrees centigrade the book talked about?
Ah.
It reaches a certain level and stays there, like in a deep pond?
Yeah, when water freezes, it freezes completely at 0, but something happens with its density between 0 and 4 degrees, which is different than almost every other object or material we're familiar with. Yeah, that I hope to get to at the very end of this lecture, otherwise it'll be the beginning of next. All right, I think I had one more. Okay, maybe you'll get this one now. Matter does not contain what? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Come on. A few scragglers there. Okay, good job. It doesn't contain heat. We talked about that. That's the internal energy transferring. It contains internal energy. Any questions about that? All right, you can put your clickers away. Thanks. So we're ready now for this formula, our guide to our thinking. Again, this is just a footnote on the bottom of page 273, but I think it sums up this chapter. The author, never mind. So heat, we represent with Q. I think you realize by now it's proportional to several things. What's one thing it's proportional to? That's whether energy is going to be transferred or not. What determines that? How much?
The other temperature.
Very good. A change in temperature. So it's proportional. And I bet you know that if something's, the difference between two objects is a lot different, the temperature, more heat will flow, right? That's it. Turn up the flame. It's hotter. Add more wood. It's hotter. Well, sure, it's going to heat up faster because energy will be transferred. More of it will be. Okay, what else do you think it's proportional to? Say again? Pressure. How so? What do you think? The more pressure. It's like if you're pushing on it more? Well, that actually it will not. That's a good thought. Because that's pressure's force over area, and we're not really forcing anything. This is kind of what drives it. Let's look at that a moment. Say you got two objects. Let's say this one's at the low temperature, and this one's at the high temperature. Which way will heat flow? High to low, this way. So heat flows. But why? Have you ever thought about it? Well, you got all these particles in here, right? And they have average translational kinetic energy. They're moving around, and they bump into each other and knock each other around. And you have particles over here. And when they're together, they can influence each other, right? You have collisions. And momentum and energy is transferred. Because when they come over here, they run into these guys, and vice versa. Which ones are moving faster on average? Yeah, this one. So the velocity's, faster. Velocity here is slower. What happens when something fast runs into something slow? Remember we did that? It's like your two billiard balls, right? This one's coming in with a velocity. Let's say they're the same mass. What will happen after they collide? Remember we did that on the air track with air carts? Well, you can do conservation of momentum, right? Review time. M1v1 plus M2v2 equals M1v1 plus M2v2. This is after, and this is before. If this guy's not moving initially, I guess we'll have to give him letters, right? Let you catch up if you're writing down. So, before, this guy has all the momentum. Because this guy has none, he's not moving. So the total momentum's wrapped up in this guy. Before. So that has to be the total after. And so it's split. So I think you can see they'll both be going, well, this one will slow down, and this one will speed up. And that's my point here. The fast ones will slow down. What happens to its temperature? Yeah, and these guys pick up speed. So the hot one gets cooler and the cold one gets warmer until when? Until they reach equilibrium. They're the same temperature. That's kind of how or why I like to think heat is being transferred. That energy's moving because it's just a bunch of microscopic collisions.
So how does friction cause heat?
How does friction cause heat? Yeah. Well, when you're pressed the particles interact.
Just like the
Yeah, with chemical bonds, as well as microscopically, things aren't smooth. And so if you have an edge that looks like this and another edge that's kind of like this, and you try to force them across, that requires work. You're putting energy in to like break these and smooth them out. And that energy, the work you put in, is converted to internal energy because you're making these things move. Heat's transferred. They get warm. So it's kind of like you're jostling them, in a sense. Okay. Now I drew this like this on purpose. This one's bigger. Think of this was a jar of water volume, and this was a smaller jar of water. To emphasize that heat still transfers from hot to cold. Which one has more internal energy? The right side or the left side?
Left side.
Are you sure? Good. Why? Because there's more of it. There's more particles. So on average, they have a lower temperature, less translational kinetic energy. But there's a whole lot more of them. So on the whole, you add all that up, the total internal energy, there'll be more here. Do you see that? Again, that doesn't determine which way heat flows. The temperature does. But it does determine how much heat will transfer. Let's say this guy starts out at, 100 degrees. And this starts out at 50 degrees. Both really hot. This is crazy. Where do you think the temperature will balance at equilibrium? Okay, I'm glad you didn't say 50. Let's start with that one because it's a little easier. Because who was saying 50 in their head? Come on. Oh, good for you. Because most people do. If they're the same material, same size, it'll balance right in the middle. Because whatever energy this one loses, it gains. It's all symmetric. But like this guy's transferring his internal energy to this guy. But let's say he transfers a packet of Q over here. Well, eventually all these will have to share it. Well, there's more of them. So on average, each little particle won't be moving as fast, won't have as large an increase in temperature as this one dropped. And it's just because there's less of it here than here. Does that make sense? So yeah, it won't end up in the middle. The temperature will be closer. This guy will change more than this guy because there's less of it. If they were equal, we'd split right in the middle. It's 75. But because there's less of it, this guy will have a larger change in temperature and this guy a less change in temperature. So it'll actually be somewhere over here more. And that depends on what those masses are. You with me?
When the left one's hotter, when it transfer back and keep transferring back again until they're pretty much the same.
Yeah, it can happen that these can cause these to move faster and make it really hot initially, but then they bump into the slower guys. And you'd think that, well, yeah, couldn't this one overshoot? He drops colder than this one, and this one shoots hotter. It might right there at the end. I mean, it might be doing a transfer, and then but it doesn't overshoot much, if at all. I mean, if you're looking at all the individuals. Because once this one gets down to the same temperature this one's at, on average, there's nothing more transferred because there's no more reason to. So, but individually, this one can be going really fast while this one's going really slow, and this one could be going slow, and this one could be going medium. But on average, the temperature will come meet in the middle or closer to one side of the other and stop at that equilibrium. So that's to help emphasize this second one. So we have, that is what drives it, kind of like the pump. But how much transfers and where it's going to end up is based on the mass. And I bet you can think of a third one that it's proportional to. We did it last time. Wood versus metal.
Density.
Close, close. But it's not called density. It also tells me, sees if anybody's read the chapter. Remember what it's called? What's that? Ooh, getting closer. Conductivity. That's how efficiently it can transfer heat through a material. So, for example, copper can conduct heat through it much easier than styrofoam. But it doesn't determine how much. Very good. This thing called specific heat. Not the speed of light, but they use C. I guess throw in this too. Specific heat capacity is what it's called. Yes?
So if we're, I mean, we talked about how it's not equal to pressure or anything else, but if it's proportional to mass, by extension, shouldn't it be proportional to everything that mass is proportional to, and then by extension, everything else? Does that make sense? So it would be proportional to pressure in that way.
By extension, yeah. This is proportional to mass. So if mass changes, and everything else that's associated might change at the same time, doesn't necessarily mean that this will change just because. So how is mass proportional to pressure?
It's not. I'm just saying that suppose if mass is equal to force or weight times gravitational energy.
Yeah, let's do that. The weight is mg, right? Yeah, force is proportional to mass. Because as this changes, that changes. However, just because, well, this is the key. This changed. So that will affect its weight, but it will also affect how heat is transferred. But that does not mean you can't make the jump that force is related to heat. They're related through this connection that if this changes because of the change in mass, then something's going to go on here too. But it's not because of force, it's because of mass. So that's, what is that, the transitive property in math? You guys remember that? If A equals B and B equals C, then A must also equal C. That doesn't work like that here. So those are the three things. This is the formula. It is exactly this. This is what I was getting to, guide to our thinking. And now I hope you understand it. That determines, is great because it works for like everything. How much heat's going to be transferred? Well, it depends on the difference in temperature, what it is, the object you're trying to transfer it to or from, and how much of it. And this just reminds me of everything we just discussed. So, go ahead.
How do you measure the specific heat?
You look it up in a table. Or if you can measure the amount of heat transferred, you can work backwards and deduce this. That's done in labs a lot. That's how they got it. They tried to capture the heat transferred to determine what specific heat is. Let's discuss that one more. I like to think of that because that's the confusing one in this, as thermal inertia. I hope you got inertia down by now. Inertia is a resistance to change in motion. Think of specific heat capacity as thermal inertia, resistance to want to change its internal energy. Because remember, heat transferring is it's either giving up internal energy or gaining internal energy. And some objects, materials, want to do that more readily than others. Example, and you know this, when I had you touch the wood versus the metal feels colder. They're the same temperature because they've had plenty of time to come to equilibrium with the room, the air in the room, but it feels colder. Because you're hotter than both of them, generally. So internal energy is being transferred out of you into them. Metals generally have a lower specific heat capacity or a less thermal resistance, thermal inertia. So they don't resist the change as much. And so that energy, it comes out of you and into the metal readily. where the wood has more thermal inertia, has a higher specific heat capacity. So it resists that change more. Does that make sense? And water is huge. It has a really big specific heat capacity. You have to put transfer a lot of energy into it before you see much of an effect in its temperature. And you know this. You put a metal, your spoon over the stove versus the water. The water takes forever to seem to come to boil, right? But the pan gets hot like that. That has a lot to do with its thermal inertia. Metals resist that change less, so the effect is seen quicker. The reverse is true also. Once something has a bunch of internal energy, think of that. Think of your pot of water versus has so much internal energy, and a block of metal that has the same internal energy. They've finally gotten up there and absorbed a lot. Which one did it take longer to get there with? The water, because it had more thermal inertia. But say once you get there, okay, now set them out here and let them cool off. Energy's transferring from them into the room, right? Who will cool off faster? Who wants to resist changing more? The water. So it'll take longer to cool off also. So things with a high thermal inertia, big specific heat capacity, take longer to heat up, and they generally take longer to cool off. There's a question up here first, I think.
I was just wondering if the specific heat capacity was directly related to the point at which a material will combust.
Oh, is it directly related to the point a material combusts? I want to say no. I've never thought of that. I have to look into that more to see if there's is a little correlation there, but I don't think they're going to be. But yeah, I have to look more into that.
What's the best conductor?
The best conductor of heat?
Yeah.
Well, that's thermal conductivity that we discussed before. This is its resistance to wanting to change, to absorb or give it up. Once it's in it, transferring through it is conductivity. So that's something different.
Okay.
Metals are generally better conductors of heat, though, also, in addition to having really low thermal inertia. And it has to do with the electrons being free. They're good conductors of electricity, too. The electrons are generally more free to move around and transfer things.
So what's the best material for conductivity?
For conductivity? Silver, maybe? Copper? They're good. So, that's an example. If you take water, I should back up because I wrote it on the board last time. I didn't talk about it. The temperature scales. Then I'll come back to this. We'll see how it relates. Were made because convenient when water freezes. They call it 0 degrees Celsius. And water boils. These are the phase changes, right? At 100 degrees. That's the Celsius centigrade. The root centa is 100 grade measure. Worked out. There's 100 divisions between that. But that were the marking points. For Fahrenheit, the United States, are we the only one left that uses Fahrenheit? 32 and 212. Again, same points. It has a little better resolution, but just a different unit scale. In science, we like to use Kelvin, and we don't say degrees Kelvin, we just say it's Kelvin. And it's an absolute scale. Water freezes at 273, I think, and 373. Sure, I'm not telling you wrong. Yeah. And that one's based on absolute 0. So think of it. Okay, notice there's a difference of 100 between here. So it's very similar to this. It's just instead of putting the 0 point where water freezes, they put it way at the back with like the lowest temperature anything could ever get to. So 273 is a big number. When you say 273 Kelvin, not degrees Kelvin.
Why is that?
Why they don't say degrees?
Yeah.
I don't know. I really don't.
I'll Google that.
Yeah. well, So what happens at zero? Well, you guys can get close. Let's work that backwards. Okay, as things get colder and colder and colder, what happens to it molecularly? Yeah, they start moving slower and slower because the average translational kinetic energy is decreasing. Internal energy is being given up. Yeah, they move slower and slower and slower. At absolute zero, that's defined as the point where you would say something has no more temperature, because it's zero, right? However, it's interesting. That doesn't mean all the little particles have to stop moving. There can still be motion. Most things are still moving. They just are not moving with translational kinetic energy. They have no more kinetic energy available to give up. That's what we refer to as absolute zero. So they still can have some internal energy, but nothing available to give up. So it's essentially that, remember, temperature is just a measure of that. So zero, absolute zero, just means they don't have a temperature. They have nothing more to give up. But that's the reference point of this scale. You guys have heard of liquid nitrogen? I'm going to bring some out at some point. That is 77 Kelvin, to give you an idea. That works out to be negative 196 degrees Celsius, negative 300 something degrees Fahrenheit. So it's really cold. But the molecules are still moving, just a lot slower. And if you touch that, there's a huge difference in temperature. So heat transfers quickly, and within a second you can freeze your tissue and kill it. It's not good to touch. So with that in mind, let's take water. Let's do time here and temperature. Okay, we'll make it easy. We'll call this 0 degrees. And this 100 Celsius. So if you take ice freezes, water freezes here. But what if you take ice and you keep making it colder? Can you do that? Can ice get colder than 0? Absolutely. What happens physically to most things when they get colder? The molecules slow down, so they're not like pushing outward as much. They're more and more sluggish, right?
Expands too, right?
They're getting colder. So the other way. Yeah, most things contract. Their density increases, right? Because it's the same matter, but in a smaller volume. So when most things get colder, their density increases. They contract. So that's what happens to ice. Once you have ice, say you got an ice cube, I'm exaggerating, but as it gets colder and colder and colder, it gets smaller and smaller. So let's say it looks something like, like that. When you get up to here, say, let's go the other way now, we're adding internal energy. What happens to the temperature while it's melting? Yeah, it stays the same. Where's that energy going? Breaking bonds. It's not going into raising the temperature, average translational kinetic energy. So the temperature doesn't change for a while. This is idealized. Okay, now it's water. What happens? Yeah, it goes up till 100, right? And what happens when it goes to steam? Stays the same for a while and then goes on up. And if you want to know how that changes, when you have a change in temperature here, here, and here, all you have to do is do this. How much water do you have? What's the specific heat capacity? Thermal inertia of water. And what's the change in temperature it's had? You know exactly how much heat it takes. Or if you put in so much heat, you know exactly how much it's going to change its temperature. That works for all objects in either direction. Now the only caveat is that formula doesn't work when you're here, does it? Because there is no change in temperature. And this is the chapter we're not covering, so I'm not holding you to this one. But there's something called the latent heat. And that's the energy going into breaking those bonds or reforming them. And so you can similarly figure out how much heat goes in or out during phase changes. That's what this formula would do for you. We're just going to deal with this one. And again, how much heat transfers or the resulting change in temperature is based on how much you have and what it's made out of. Because everything reacts a little differently. So, places near the ocean, generally, they have a lot more moderate temperatures, don't they? Now you know why. Water has a huge thermal inertia. So when the weather drops and it comes to winter, well, the water, and that's a big bank of water too, takes a lot longer to cool down. So it will retain internal energy. And the water can easily be warmer than the outside air in winter. And vice versa in the summer. In the summer, things heat up. But it wants to resist changing for a while so the water can stay cooler. And when the winds blow across the water either way, it moderates the temperature and keeps it from being less extreme. Keeps it from being more extreme. It is less extreme. So that's why places, coastal places, generally have nicer weather and people like going there. Let's see. This is good. We've covered a lot. So let's do the water thing. Lead up to it here. So these are just some thermometer examples. You guys know what thermometers are. I thought you'd enjoy. This is your classic. Has mercury, and this one has alcohol. And how they work is, you know now, if the air is hotter in here, heat transfers to the alcohol. And it changes its temperature. And when it heats up, they're moving faster, it expands. Its density decreases. And if it expands in this little tube inside there, it raises up. And you can calibrate that. Here's an example. I just filled this full of green water. And so if I put my hand on top, what will happen? Why does the pressure change? It's closed here and it's closed here. So air won't be moving from outside to inside or vice versa. But there could be a change in pressure inside. It's caused by heat transfer. I'm warmer than this, because this is probably at room temperature now, and we're warmer than room temperature. So heat will transfer out of me and into it. That'll heat up the air and the glass and the air inside, right? And if it starts moving faster, that will increase the pressure inside. So what will happen to the level of the water? It goes down. And if I was hotter, got to do the Karate Kid thing. You guys remember that movie? But that's basically how a thermometer works. Most thermometers, the classic kind. Let's see if that's warm enough. Let's exaggerate. Sure, it goes down. So it's just they're expanding. What would happen if glass and water had the same thermal inertia? They'd expand at the same rate. Excellent. So as one expanded or contracted, so would the other in unison, simultaneously, and you wouldn't notice a difference. So you can't make thermometers out of a liquid and a glass, with the same specific heat capacity. That would stink. What you do want to make a concrete building that's reinforced with steel rods, right, to give it strength. You want those to expand at a similar rate. Or when one expands and the other doesn't, it's going to cause tension. Here's two metals. One on one side, one on the other, brass and steel. They have different thermal inertias, specific heat capacities, so they expand and contract differently with the same heat input. One expands faster than the other. It gets longer. The only way for it to be longer and this one shorter is for it to bend. And you can see as it cools off, it goes back. You can use those as thermostats. These things, you can coil them up even because of that expansion and contraction. You got a dial now, right? That's proportional to the temperature change. Or this one. Just because things expand and contract. What do you think will happen when I see this one? We have a ring and a hoop. It fits through. If I heat up the ring, what do you think will happen? You think the ball will go through or not? Ta-da! Some people think the hole gets smaller. But no, it's expanding, right? So even the hole expands. Or think of it this way. If you stretch the ring out into a straight bar and you heat it up, it's going to expand. If you formed a ring again, it just makes a bigger ring. What if we heat up the ball? Well, let's do it. It's got more mass for the same material. So I need to apply more heat, transfer more internal energy to it. All right, what do you think, Ron?
It won't fit.
You're right. It's a lot harder. As this continues to cool, it will contract. And at some point, yeah, this won't fit through. Oh, there we go. Well, just make it. So the ball expanded, but right now they're both hot. So with water, let me at least touch on it, and we'll continue more. Look at it up in your book. Something really cool happens with water, though. Right here. During the time it takes to freeze or melt. This is one of the few substances, at least the common substance, that from 0 degrees to 4 degrees Celsius, it goes the other way. So water is coming down from 100 degrees and it gets to 4 degrees. Its density actually, instead of getting smaller, density increasing and it getting smaller and smaller and smaller, at 4 degrees it actually begins to expand. And ice is actually less dense than water. You know this because it floats, right? So in this region, something's going on. And they got good pictures in your book. Water is kind of like the molecules. They can move around. They're random. They can get packed tightly. Ice forms crystals that are hexagons. 1, 2, 3, 4, 5, 6. Like that. And another one. You get the idea. And in this structure, they actually are spaced apart more. So in water, they can be closely packed. It gets to ice that's more farther spaced apart. It actually expands. But it takes time. It doesn't do it all at once. When you have both of these together, you kind of have this ice slushy. And look, overall, you have some of it like this. So it's less dense than water because you have some of this in there. But it's more dense than ice, all ice, because you have some of this in there. And so there's this funky region in here that we'll discuss some of the effects of that next time, as well as chapter 16. All right.